let's take a look at the mechanism for electrophilic aromatic substitution. The first step is to make the electrophile, and to do that we're going to react our bromine with the FeBr3 Lewis acid, and we produce this species, which allows us then to target this bromine as our electrophile, losing the FeBr4 anion. So we're going to treat that end bromine as the generic electrophile, and benzene can attack, losing a leaving group, again FeBr4 minus, just like with additions to alkenes. When we add an electrophile, we get a positive charge on one side of the alkene and our newly formed bond and atom, our group, on the other side of the alkene. And then I have FeBr4 minus right here as my leaving group. That's what we get from this red arrow right there. There is a hydrogen here. I like to draw that so I can keep track of it. I'm going to need to use that later. But right now I want to show why this reaction is favorable. And the reason is because we have several opportunities for resonance. Hopefully you'll recognize some of these resonance structures from first semester organic chemistry. So we have 3 resonance structures in this example, and in later examples in this chapter we will see that there's potential for having more than 3 resonance structures. And now we're ready to form the final product. We need to reform the aromatic nature of the benzene ring, and to do that we need to lose this hydrogen here that is causing this carbon to be tetrahedral. We can't form an aromatic ring if we have a tetrahedral carbon in that ring. So we need to get rid of that hydrogen. We're going to use the negatively charged bromide from the FeBr4. So I'm going to redraw that here so I can use one of the bonds. So I can take this iron-bromine bond, grab the hydrogen in a proton transfer mechanism, take the CH bond, put it back in the position of the pi bond, and that will generate the aromatic ring, except that now we have a bromine on the bottom on the bottom carbon, not just a hydrogen. I also have HBr. I just made that with my proton transfer mechanism, and I have FeBr3, my catalyst, that can be reused to regenerate this species here that is used to install the bromine as the electrophile. So this is the general mechanism for electrophilic aromatic substitution. And as we add other substituents to the aromatic ring, we can gain 1 or more additional resonance structures here, and those structures can either help us cause the reaction to go quicker and favor certain locations on the ring, or they potentially could hinder the reaction, causing it to go slower, and that's going to be the topic of some upcoming videos.